Okay, so welcome back to page 6 of the review, the final exam. We'll get cracking right away here. I don't think this is going to be a very long one. A little shorter than some of the other pages. So when we start off with this problem, you'll notice yet again, I have that scenario where I gave you 2 lines for the potential of 2 triangles because I do have 2 sides and an angle. So I guess it's plausible that there could be both of them, but let's just draw the triangle because remember, 2 sides and an angle doesn't always mean angle side side. It could also mean side angle side. So I, again, just encourage people to go ahead and draw the figure as best they can, as quickly as they can. And I don't really pay a lot of attention as to what order things are in unless I think it's angle side side. And this could be. So I put 48 degrees here. That puts side B across from capital B, and it puts side C across from capital C. So this is actually side angle side story. So that tells me this is not ambiguous. There is only one triangle. You can't get 2 triangles out of a side angle side. But we do have to remember that this is actually one of those scenarios where this is not going to work with law of sines, because if you try to set this up, you would say then that the sine of 48 over A would be the same as sine of C over 13. And we definitely have a problem there because we have too many variables, and no matter what we do, it's going to happen. So what we're going to do is we're going to go with the other things. So the classic way we write what's called the law of cosines is we start with c squared, and we go with a squared plus b squared. It's the one that kind of looks like the Pythagorean theorem. But it isn't, because the Pythagorean theorem is only relevant for right triangles. It's the only place you can use it. So we have this little qualifier that goes in like that. And this is the little penalty that you pay for using a triangle that is not a right triangle. That's not going to work for this one, because really the way these are set up is whatever angle and side that you have that are across from each other is what needs to go here and here. But that's not what we are looking for. We actually are wanting to deal with, I'll use yellow. I want this angle and this side to be related to each other. So I'm going to tweak that formula a bit and start with a squared equals b squared plus c squared. Now, format-wise, it's the same as what we have. So we go minus 2bc. And then cosine of the angle that it's across from, which again is angle A. So we just basically the sum of the 2 squares, notice the AB, the BC. And so we should be pretty well good to go. And honestly, side angle side is my favorite one to do in these cases because it just is so nice, because B is 5, so B squared. C is 13, so we have 169. And we have our 5 and our 13, like that. And then the cosine of A, which is the cosine of 48. And in this particular scenario, it's just all sitting there ready to go, which makes it really, really nice. So provided that we're in degree mode, we can literally type the whole thing in one line. And hit enter. Now keep in mind that is a squared. That is not a itself. So I now know that a squared is 107.013. So I'll just take a quick square root of that number, and I got 10.345. 10.345. I'm going to put that one right here. And in fact, I like to store that in my calculator so I'll have it for later use, because as it turns out, I have something that's really, really nice. I already wrote this down right here. Remember a minute ago, I said that the sine of 48 over A is the sine of C over 13. Well, A is no longer an unknown value. I now know that that is the number 10.3445 or 347. Anyway, so we go like that. So we're getting pretty good. Let's multiply both. So let's take the sine of 48. Let's divide that by A, because remember that's what this is. So now I have the left side of this equation is this ugly little decimal. Let's multiply both sides by 13. And so now what I'm down to is that the sine of C is 0.933. That's actually a really good thing, because now if I take the inverse sine, I'm looking at 69.05 degrees would be the measure of angle C. And keep in mind, I don't always do this, but sometimes I'll use the Greek symbols for alpha, beta, and gamma. And so there we go. We've got that. And so the only one that we have left to figure out is we need to figure out what beta is, but we already got a 48-degree angle. And then we need to take that away from 180. And I did do that backwards on purpose, because I just kind of tend to do that myself because I knew it was a positive anyway. So we've solved the triangle. We found all the angles. And that's typically what happens in an SAS story, is that you use the law of cosines once and you use the law of sines once. I didn't put a side, side, side in here. It's a little harder to do, but it does the same thing. We do a law of sines once, and then a law of cosines once, and then a law of sines once. And also what I would say is the difference here is we had to use we didn't have to do anything fancy. On the law of sines, you do have to use an inverse cosine, and you have to be very careful with your order of operations. Okay, number 32. Now, I don't know that we've ever done one of these problems, but what I have is that I've got a circle. And again, I am not going to really even try to draw the icosagon, which is a 20-sided polygon that's inside this circle. But as it comes across, I'm just going to draw a few of those pieces. I would have this figure that has 20 of these sides, and it's inside a circle that is of radius 16. Okay, so I'm just going to put a 16 here and here. Now, what I'm going to do really quick is I'm going to use the fact that if we have 360 degrees in the center of this circle right here, and I'm breaking it up into 20 little subparts as we go our way around, 360 over 20 is looking at 18 degrees. So that's what the central angle is. Now, this is actually a really, really nice problem, because if I wanted to find the area of the triangle, one of the things that we mentioned in the previous video is that if you ever have a side angle side story, then the only thing you have to do to find the area of a triangle is do 1/2 the product of the two sides times the sine of the angle in the middle. So that's going to be fairly easy to get. So I'm going to take 1/2 times my 2/16 times the sine of 18, and I just found the area of the triangle is 39.554. Now, let's go back and read the question, because it didn't ask me to find the area of that triangle. It asked me to find the area between the circle and the polygon. So what I'm going to do is I'm going to go ahead and find the area of the icosagon. And of course, the icosagon would simply be comprised of 20 of these triangles as it radiates out from the center. So let's just multiply by 20. And now I'm up to 791. That wasn't too bad. Now, we're still not there, because it said let's find the area between those two. So we're looking for the sum of all of these little pieces in here as we work our way around. And there's all sorts of ways to do this, but I think the easiest thing would be to find the area of the circle itself, which is pi r squared, where in our case, r was the number 16. So that's fairly easy to do. So what I need to do is I'm going to store that as a, so I have it for a second from now, pi r squared. Now again, I'm doing this kind of the long and slow method, but you could do it faster, because it doesn't really say that we needed to write each of these numbers down as we went. We could have just done this all in one shot, but pretty clearly all I need to do to find the area between the two is to subtract. So I'm going to take that 804 and let's subtract that 791 that I have stored. And so the area between those two, so the area between is 13.164 units squared. Oh, in this case, it's specifically centimeters. Awesome. So we're kind of done with that. So that kind of polishes up all of that unit, and now we have a quick transition into polar. So remember, in this, the typical way that we do mathematics, we give you values of x and y, which is what has been given in each one of those things. So when we're talking about number 33, we're saying let's take things that look vertical and horizontal, just going back and forth, up and down on 90-degree angles, and let's convert that to a radius and an angle. And so we have three quick formulas that we know. One of those is that if you actually set this up as follows and pick some random value xy, this would be, of course, x-axis, y-axis. This would be what we would call the radius, or the distance from the origin, and here is theta. So basic trig says the cosine is adjacent over hypotenuse, and so if you follow that logic, which we did in class, I'm not going to do the whole thing again, it just leads you to the statement that x is always r cosine theta. It also leads you to the statement that y is always r sine theta, and last, x squared plus y squared is r squared. So these are the three big magic formulas that we want to hold on to that are going to be very, very helpful. And it really helps in problem C. So if I went to the right 5 and down 2, the Pythagorean theorem, 5 squared is 25, 2 squared is 4. So if we took those two things together, I would get 29, and that would tell me then that the radius from the origin down is root 29. And you can see I went out of order here on purpose, but because I wanted to demonstrate these formulas that are right here. Now, if we have that right, then all I have to do is go to my angle button on my calculator, which again was second apps. Number 6 is kind of a quick method to do that, and I just hit 5, and then I hit the comma button, which is right below sine, -2, and I say, hey, I'm looking for the angle associated with that, and my calculator says -21.801 degrees. Now, I could have solved that same problem in radians, and that would have led me to the same story as root 29, but I would not put a degree sign. I would just say -0.381. Now, just FYI, I could have also found that angle by taking an inverse tangent of -2/5. And it gives me exactly the same number. The downside is that inverses sometimes are tricky because of what quadrant they have to be defined in. And so I tend to like to do the RP theta thing because it makes sure that I put it in the correct quadrant. Now, I waited for a second because on these two problems, there is a piece of memorization. So I could use these ideas right here, but I don't. I don't really tend to use those because I want to use when we think of special right triangles. And so what I hope you realize is that if you have a 6 and a 6, then that means that hypotenuse or radius is 6 roots of 2, which is just a fact that we have utilized for a long time, all the way back since math 2, did it again in algebra 2. Now, if you needed to, we could do that. 36 plus 36 is 72. The square root of 72 is a pretty nice number because it's, well, 36 times 2, and the square root of 36 is 6. So, I mean, we could do that, but I mean, it's just sort of a waste of time if we know the answer. And then last, that is a 45-degree angle, also known as pi over 4, because again, any time a 45-degree angle has to be that. You could also think through your unit circle and see that the tangent is 1. But because it's not in the correct place, we want to rotate down into the third quadrant. And this would have been 4 pi over 4 plus 1 more would make 5 pi over 4. Now, instead of that, what we could also do is we could chronicle this as pi over 4, but have a radius of -6 roots of 2. Like, is it turn to that first quadrant and then go backwards into the appropriate quadrant? Because remember, in polar, we have an infinite number of answers. You know, I could have said, hey, let's go 6 roots of 2, but let's do so by rotating down 3 pi over 4. So just lots, and all three of these answers are great answers. And so the last one of this video, left 7 and up 7 roots of 3. Anytime you see a number and that number with that roots of 3, that's like a 30, 60, 90. That's like auto. We should know that that makes the hypotenuse 14. It's just double. That's easy. So I know that my radius is 14. And then last but not least, I just look for the easiest ratio and I see that the cosine is a half. You see it? See how the cosine is a half? And I know cosine is a half at some kind of pi over 3. And I won't do a whole bunch of answers this time. I'm just going to give you the one. But that would be 2 pi over 3 because this place would be 3 pi over 3. And so I needed to rotate just a little bit less to put it into the proper quadrant. And closing real quick, if you had the time on your test and you're like, I'm not so sure I did all this stuff right, you could come in here and check your answers very easily by saying, well, did I do this right? Let's see, R, 14, cosine 2 pi over 3, enter, should be -7. See, it worked. And then if I tried it again, but I did R, there we go, sine of 2 pi over 3, I'm going to get something ugly, but that number is 7 roots of 3. So I could type it in when I'm all done to make sure that I actually did the right work and that I haven't made a silly mistake like calling this a pi over 6 or making it 4 pi over 3 or some incorrect angle. So anyway, and clearly we could do the same thing here. I could type in R cosine of this guy to check the X, R sine of this guy to check the Y, make sure I got those numbers right there. But there we go. I'll see you back for the last couple pages soon. All right, bye-bye.